Welcome back. In today's lecture, we'll start the consideration of approximations in engineering. We will try to understand how to make and justify approximation in engineering sciences. The mathematical equations and boundary conditions that govern most of the engineering situations are quite complex and defy closed form analytic solutions. The limited number of exact solutions available have been obtained for some very simple geometries and for very restrictive conditions. In such cases, one or more of the terms from the governing equations drop out because of some or the other simplifying feature, such that in fluid mechanics and heat transfer, it is common to make assumptions of steady flows, fully developed flows, one-dimensional or two-dimensional flows, low viscosity flows, negligible viscosity flows. But such features are not encountered in general. The solutions obtained through these simplifications are so cherished that we like to extend them to realistic situations where those conditions are not met exactly. This is what we mean by approximate solutions. If we were predicting the global weather using thousands of equations and a host of data collected over a long period of time and using a supercomputer to solve it, and an onlooker suggested that we are making a mistake by not including the effects of the flapping of the wings of a distant butterfly several weeks earlier, we would simply have laughed it off, because we believe that small causes produce small effects, and we believe that the flapping of wings of a butterfly is a small cause. But is it a small cause? Edward Lorenz in 1961 found out that a very simple rounding off of initial conditions while predicting the weather through a numerical model resulted in a massive deviation in prediction of weather about 2 months later. Here are some results. We obtained two solutions to a given problem where the two initial points differ by only 0.00001, such a little difference. And if we have two runs, one a blue run and a green run, then the difference of the values predicted by the two runs with two different initial conditions, differing only by a very small amount, 0.00001. Looks like this. Initially, for a very long period, the two solutions are the same. But then they start deviating. And the deviations are quite big, showing that the solutions can be very different even if the initial conditions differ only very slightly. One meteorologist, when he looked at the results like these, remarked that if the theory was correct, one flap of a seagull's wing would be enough to alter the course of the weather forever. The controversy has not yet been released. But as someone said, that the most recent evidence seemed to favor the seagulls. Let's look at a double pendulum, two pendulums in series. In this video, we see that initially we have same configuration in all the 6 setups. the setups are identical, and when they are released, they have the same initial conditions. But as the time passes, the small deviations start appearing. And even before 20 seconds have elapsed, the motions of all 6 pendulums is entirely different from one another. There's a whole theory of deterministic chaos that governs this. Chaos theory states that within the apparent randomness of chaotic complex systems, there are underlying patterns, interconnections, constant feedback loops, repetitions, self-similarity, fractals, and self-organization. Deterministic chaos is where the present determines the future. But the approximate present does not approximately determine the future. Of course, the present determines the future. The initial conditions determine what is going to take place later. But slightest approximation in the present condition can lead to significant departures. Again, approximate present does not approximately represent the future. But still, the practice of engineering proceeds on the principle that small causes produce small effects. We assume this to be true, and we shall persist with this here till something breaks down. And then we'll investigate what is happening. It soon will. And we'll see many cases where this does. We must approximate. We cannot find exact results because we cannot model all effects. The kind of forces that are present in a simple phenomena cannot all be written down in the equations. We also cannot model all boundary conditions exactly. In fact, we cannot model the geometry of a problem exactly. There's always some assumptions. If nothing else, we assume the material is uniform. So we must approximate. So we must have a basis on which we can decide if our approximations are going to work or they are not going to work. And we start with the approximations of the governing equations. In order to establish which terms in the governing equations are negligible, their magnitudes need to be estimated. One powerful method of making such estimate is to normalize each variable by scaling it with its characteristic value. If the characterizing values of the quantities are chosen properly, the normalized variables are then expected to be of order unity, that is, except at certain isolated locations in the flow field. The values of the transformed variables are expected to be neither large nor very small compared to unity. Further, it is hoped that the dimensionless derivatives of the various physical quantities appearing in the equations are also of order unity. This last is a very important hope, very important requirement. Consider an LCR circuit, the voltage drop across the inductance plus the voltage drop across the capacitance plus that across the resistance. must sum up to the alternating voltage that is applied to the system. The resulting equation is here. If I write the current as dq by dt, where q is the instantaneous charge on the capacitor, then this equation converts to this. Now, we start with not dimensionalizing it, or rather normalizing it. This equation, the solution of this equation is of the form that q is q naught sine omega t minus phi, where q naught is the amplitude of the varying charge on the capacitor. So, while normalizing, we introduce the non-dimensional variables q star is equal to q divided by some characteristic value qc for the dependent variable, and for the independent variable time we introduce t star is t by tc. If we choose qc and tc correctly, then the resulting q star and t star should be of order 1 throughout the phenomena that we are discussing. The characteristic time Tc must be related to omega, the frequency of the voltage that we apply. We may choose Tc as 1 over omega, so that T star is omega t. Qc may be the amplitude q naught of the instantaneous charge on the capacitor. And if we do this, the equation becomes LC omega square d square q by dt star square plus RC omega dq star by dt star plus q star is equal to C V naught by q naught sine t star. Besides introducing the two normalized variables, we have manipulated the equation such that the coefficient of one term has become unity. Now, we hope that this non-dimensional dependent variable, this non-dimensional independent variable, and these non-dimensional derivatives of the dependent variable are of order 1. If they are of order 1, then this coefficient and this coefficient and this coefficient measures the relative magnitude of the various quantities in these terms. So, the ratio of the voltage drop across the inductance to the voltage drop across the capacitance is LC omega square. But let us look at this expectation that the derivatives are also of order 1 in a little more details. Consider a problem in which a function f is given by an ordinary differential equation. If we normalize f and x by their maximum values, we may get a plot of f star and x star like shown here. It can be shown that for the function and the derivative to be of order 1, the function and its derivatives must be continuous and differentiable up to an order 1 lower than that appearing in the differential equation. This means that the function can be normalized since it is bounded, and that the domain of integration can be made approximately unity by normalization. There are often good grounds for assuming these conditions. Further, look at df star divided by dx star. If the function is well behaved as shown, then df star divided by dx star is approximately equal to 1 everywhere. Similarly, the second derivative of star with x star would definitely be less than the typical value of df star by dx star minus 0 divided by 1 minus 0, the range of x star, which is 1. So that the second derivative is also of order 1. Similarly, if the function is differentiable, the higher order derivatives normalized would also be of order 1. This implies that the nth derivative of function f, the original function f, non-normalized with respect to x is less than the characteristic value of f divided by the characteristic value of x raised to power n. Thus, if the function is well behaved, not only the variables but their derivatives are also rendered of order 1 when we normalize the variables with the quantities that are truly characteristics of these variables. Such estimates are termed as smooth estimates. But not all estimates are smooth. F star x star plot could be like this. And if this is the case, there is no single estimate that is valid for the entire range of x star. For the range 0 to epsilon, in this range, df star by dx star is like 1 over epsilon. And if epsilon is small compared to 1, this is pretty large. And one can show quite easily that the second derivative d square f star by dx star squared should be like 1 over epsilon delta, where delta is the width of this transition, and that would be like 1 over epsilon square. But in this larger range from epsilon to 1, the first derivative is quite small, as is the second derivative. This is an example where one single estimate of the derivatives would not work for the entire range of the values of x star. We would assume in most discussions that the function is well behaved, like in the previous case, till we run into a problem, and then we look if something like this is happening. This was famously done by Ludwig Prandtl at the turn of the last century, when he introduced the concept of boundary layer, a thin layer where the gradients are very large when for the rest of the regions the gradients are well behaved. We will discuss this a little later. We could have variation of a star with X star that look something like this. Here again, normalizing the variables does not ensure that the derivatives are normalized too. So what do we do then? We assume that the functions are of first type, well behaved, and that the estimates are smooth, but we should be constantly on the lookout for trouble. And we are sure to find it often enough. Let's do one more example where we introduce the concept of approximations. This is the flow past a circular cylinder of an incompressible fluid. The free stream has a pulsating velocity V naught sine t by tau, where tau is a given time period. The pressure for stream is P naught. The diameter of the cylinder is d. Is a two-dimensional flow. Independent variables are x, z, and t. Let's use d, the diameter, as the characteristic length, so that x star is x by d, z star is z by d, and we can use tau as the characteristic time, so that t star, the normalized time, is t by tau. The dependent variable u and w along x and z direction are normalized with respect to the amplitude of the free stream velocity v naught, so that we define u star is u by v naught, w star is w by v naught, and we define a non-dimensional pressure, another dependent quantity, as P star is equal to P by P naught. If we introduce this transformation in the equations for the governing flow, the equations for the governing flow include continuity equation and the Navier-Stokes equation. The equations become this. For incompressible flow, this is the continuity equation, and this is the Navier-Stokes equation in the normalized variables: x star, z star, t star, u star, w star, and p star. This is the unsteady flow term. This is the convective acceleration term. This is the pressure force term. This is the gravity force term, and this is the viscous force term. We have to normalize the boundary conditions as well, and these are the resulting boundary conditions. So this is what we had. Now these terms which are put in boxes are the variables and their derivatives. If we have chosen our characterizing quantities properly, then these are expected to be order 1. As I said before, the first term is the unsteady force term, the second is the convective acceleration term, the third term is the pressure term, the gravity term, and the viscous terms. Now if this and this are of order 1, the coefficient of the unsteady term can then be seen as the ratio of the characteristic unsteady force divided by the convective force where the coefficient is 1. So d by V naught tau can be interpreted as the ratio of the unsteady acceleration term divided by the convective acceleration term in this equation where the coefficient of the convective acceleration is 1. Similarly, this is interpreted as the ratio of the pressure term to the inertial term, the convective inertial term. And as had been discussed earlier, this is given the name 1 over Euler number. The next can be interpreted as the ratio of the gravity force to the inertial force, and this is seen as 1 over Froude number squared. And the last coefficient is the inverse of Reynolds number and is the ratio of viscous force to inertial force. So if any of these coefficients is small compared to 1, that is compared to the convective acceleration term, then the corresponding term can be neglected from the governing equation. This is the primary tool that we used for estimating the terms and making approximations. Here we have made the coefficient of this term. The last term was the viscous force term. We have made the coefficient of this term to be 1. And then this is the ratio of inertial force to viscous force. This is the ratio of inertial force convective to the viscous force. This for the pressure to viscous force, and this gravity to viscous force. We had discussed earlier that in situations where the cavitation and the free surface effects are not present, we could introduce a modified pressure script P by this expression, and so that the resulting equations absorbs the pressure and gravity term into one term, and this is the resulting equation. This then is the ratio of the unsteady term to the viscous term. This is inertial acceleration to the viscous force term. This is pressure and gravity or non-gravitational pressure term to the viscous term, and the coefficient of viscous term is 1. So this is the equation that we obtained last year. Now, if we have a steady low Reynolds number flow, of course the flow is steady, so the unsteady term, which was the first term in the last equation, drops out, and this is the equation that results. Now the flow Reynolds number is low compared to 1. If it is small compared to 1, then this term, which is the Reynolds number itself, this coefficient is less than 1. This coefficient is 1. So we can drop this in comparison to this. And if we do this, this is what the resulting equation is. The pressure forces balance the viscous forces. In terms of dimensional variable, this equation becomes this. The Stokes equation. And this is the form that you see in the Stokes equation. It is valid for a Reynolds number much less than 1. You may note that this equation is linear in the velocity variable. The Navier-Stokes equation is nonlinear in the convective acceleration term v dot del v, and that term drops out in this low Reynolds number flow equation. So this equation is linear in the velocity variable, which affords enormous simplification in its solution. The linearity of this equation, along with those of the applicable boundary conditions, permits us the superposition of elementary solutions to obtain more complex solutions. The Stokes law is the low Reynolds number flow, Reynolds number much less than 1, past a sphere. It's called a creeping flow in fluid mechanics. The solution is possible, but it's not easy. We give here the solution in the spherical polar coordinates. The r velocity is like this, the theta velocity is like this, and the pressure is given by this expression. This Stokes law at low Reynolds number are very different from the inviscid flows. Look at the velocity profile on the shoulder in the Stokes law. This is very different from the velocity profiles in an inviscid flow, where viscosity was negligible. The Stokes law is viscosity dominated flow, while this flow is a flow in which the viscosity is 0. The nature of the velocity profile at the shoulder is entirely different. And this can be obtained as exact solution. This also can be obtained as exact solutions under the specified conditions. The flow pattern in Stokes law is completely symmetrical. The streamlines are the same whether the flow approaches the sphere from the left or from the right. Even though the flow pattern is symmetrical, the pressure distribution is anti-symmetrical. Thus, while the pressure is maximum at the nose of the sphere, it is minimum at the tail, even though the velocity is the same at 2 points. This observation is also in marked contrast to the behavior at large Reynolds number flow. Bernoulli equation does not apply. Even though the velocities are the same at 2 points, the pressures are entirely different. The fluid velocity is significantly lower than the free stream value V naught over a considerable distance from the shoulder. In fact, we need to go out to 16th time the radius before the velocity approaches 99% of the free stream velocity V naught. This means that the effect of the presence of sphere is felt over large distances. This too is unlike that in the case of high Reynolds number flow, where the velocity approaches V naught in very short distances, less than 2 radius of the sphere. Because of this influence of the sphere over large distances, small particles moving at low Reynolds number interact strongly with one another. That is, the motion of a particle is affected by the presence of other particles, even when the separation is large compared to their diameters. This too is in sharp contrast to the motion of larger particles which have almost no such interaction. Also look at this equation. Since the two terms must be retained in this equation, this coefficient should be order 1. Delta P naught is the characteristic pressure difference. So, to make this coefficient 1, delta P naught should be like mu V naught by d. From your fluid mechanics, you may recall that the characteristic pressure difference in large Reynolds number flow is 1/2 rho V naught square. Here it is mu V naught d. This was to be expected since the pressure forces balance the viscous forces. Hence, the two terms in the equation must be of the same order. Further, the total pressure and shear forces acting on the sphere in the horizontal direction are obtained as twice pi mu RV naught and 4 pi mu RV naught respectively. So that the total drag experienced by the sphere is the sum of the two, that is 6 pi mu RV naught. And the drag coefficient defined as drag over 1/2 rho V naught square A, the traditional definition of the drag coefficient, is like 24 by Reynolds number based on diameter. So, the approximation of flows where the velocity is very small, which is marked by the values of Reynolds number to be much less than 1. If that is the case, we can drop the convective acceleration term, and then the viscous forces are balanced by the pressure forces. The resulting equations can be solved with a bit of advanced mathematics, and results can be obtained which turn out to be correct representation of experimentally obtained results at such low values of Reynolds numbers. Note that the drag in the Stokes formula 6 pi mu RV naught does not depend upon the density of the fluid, confirming that the inertia of the fluid is unimportant for the low Reynolds number flow, where the inertial terms was dropped from the equation. And that's why the density does not occur in the formula for drag. This should give you some confidence in the way we propose to make approximations. For studying the large Reynolds number flow, we manipulate the terms such that the coefficient of the convective acceleration is 1, and then the coefficient of the viscous term becomes 1 over Re, 1 over Reynolds number. When Reynolds number is large, clearly this drops out. The boundary conditions are these, but we sense trouble. There are two conditions, boundary conditions on velocity, but this equation has only one derivative of velocity. This cannot take two boundary conditions in velocity, it can take only one boundary condition in velocity. A boundary condition is upstream and a boundary condition on the surface of the sphere. So the simple-minded approximation method that we introduced has broken down so quickly, the resulting equation does not satisfy the boundary conditions. In fact, if we drop the viscosity term, then this boundary condition of no slip on the surface of the body cannot be satisfied. But it is an essential boundary condition. So something has broken down. This is what is irregular perturbation, and this is what Prandtl responded to. And we will see later that we can handle this, and we will develop methods for doing so. Thank you very much.